Hi Spring fans, welcome to another installment of Spring Tips. In this one, we're going to look at the question I'm often given, which is, hey, I have a brand new application. I'm using the new reactive support that you've hopefully heard me talk about for the last 2+ odd years, and the Spring team at large, and you've seen countless blogs on the Spring IO blog, and a good deal many videos on the topic from the various conferences, from the Spring One platform shows. I mean, and not to mention, literally hundreds of conferences around the world. I mean, hopefully at this point you're persuaded, right? I hope that you can appreciate that reactive programming gives you the ability to build better software faster. It gives you the ability to more precisely, more technically build applications that take advantage of asynchronous I/O to support better throughput, better scalability. So you can handle more transactions with the same computer because you're no longer sitting on a given thread, monopolizing that thread, making it impossible for others to use it. By doing this, you're able to build software that can handle more users, right, with the same cost. Or you can have your data center built, right? Instead of doubling the number of users, you can have it. I'm using half and 2x as simple numbers, but the point is you can either handle more users for the same cost, or you can handle the same users for less cost, right? And that's one of the big benefits here, and it allows you to scale out, right? It allows you to handle greater capacity of a greater number of requests, and this is particularly important when you move to microservices, into IoT, into big data, where you've got an increasingly larger amount of data being connected over the network through network buffers in terms of input and output. Reactive programming is all about input and output, all about, I suppose you could talk about some of the other use cases, right? There's the fact that reactive programming gives you the ability to better reason about errors in your processing flow, your stream of data. It gives you a functional style way to manipulate streams of data as well. That's more elegant. It also gives you a compositional model that's based on the decoupling of, or the sort of separation of the assembly of the processing pipeline from the subscription of the processing pipeline. We say that the assembly of the pipeline is cold, right? It's a cold stream of data. It's like a series of pipes that have been connected together. But until you pour water into those pipes, that's the subscription or execution time. Then we say that is a cold stream. Once there's water in the pipes, then it's a hot stream, right? You're now in execution time. So you define the pipeline, data goes through it, and then these two things can happen separately. You can define the pipeline now, and then the data can flow through the pipeline an hour from now, right? The benefit of that is that there's an opportunity there to intervene, right? You can actually have the operators, you can have the scheduler, you can have the framework that's aware of this pipeline, and it's aware of how these things stick together. You can have it intervene on your behalf, and so it can reassemble things. It can add extra steps, for example, for auditing or for debugging. It can do all sorts of interesting things. It can also rearrange things if it sees possible optimizations. It might be able to fuse certain operators that would be, two steps that could be made into one, because you've got sort of a makeshift compiler kind of thing going on behind the scenes there. Not really, but there's optimizations there, right? So there's a lot of opportunities by moving to reactive programming, and by moving to a framework that gives you the ability to think about things in this way. And because of that, you also have this more interesting opportunity in a single place to sort of deal with and think about errors. There's also I think it's a natural way to think about integration, because if you have to think about how you interact with different systems, if you had to pick one modality, pick asynchronous, right? I want to connect two different types of data out there. Some systems are easily integrated with in terms of a synchronous API, and some are easily integrated in a asynchronous API. But you cannot synthesize or fake blocking interactions. Non-blocking interactions. You can't fake asynchronous interactions with a synchronous integration. So if I want to talk to something that publishes messages asynchronously, there's no way to do that except for asynchronously. On the other hand, if I want to take something that is asynchronous and then consume it in a blocking way, I can do that. I can simulate that, right? So if you have to pick one type, pick asynchronous first. And so when you're dealing with the Reactor API and with reactive APIs, you're dealing with asynchronous APIs. And this gives you a nice way to model the world. You can deal with the world in terms of this one kind of stuff, this reactive stream of data. So whether you're talking to a REST API or getting data from a database, or doing messaging, or you're doing WebSockets, or you're doing application JSON, just 5 records, whatever you're doing, you can deal with it in terms of this publisher API that is core to the reactive streams spec, okay? And you can deal with it in terms of the operators that come with Reactor, and Reactor makes it easy to build these sort of reactive applications. Now, I've talked a good deal about all this stuff before. I don't really want to get too deep into that, but in this installment of Spring Tips, my friends, we're going to look at what it is to build applications that are reactive, and what it is to debug them, right? What are some of the opportunities we have for isolating issues in our reactive applications? Because as I've just established, reactive applications are, at least in terms of the programming model, asynchronous by default. So we're going to build a new application here at start.spring.io. We're going to call this debugging Reactor, okay? And we're just going to use, I'm going to use the reactive web support. I don't really want the web server. I don't care about the web server. I just want something that'll bring in Reactor and all that stuff with it. And also this has the benefit of starting up a web server. And so it'll keep the Java process running. Otherwise, my asynchronous APIs, which are, they won't keep the process running unless I do something to make them all daemons. So I'll just use that to get around that issue, okay? And then we're just going to hit generate. There we go, okay? So I think this might be the simplest demo in terms of dependencies that I've ever done for you, my fine friends. So that's kind of interesting. Now that I think of it, I didn't even add Lombok. How cool is that? Maybe I should have added Lombok. I don't know. You'll see that I'll add some dependencies. So maybe I shouldn't get ahead of myself. What we're going to do is to just demonstrate some of the opportunities here for debugging things with IntelliJ. What we want, there we go. There's my application. What we want is, here we go. We want to make our lives easier, right? And I'll be the first to admit that moving to an asynchronous world where execution of processing can jump from one thread to another with ease and almost shocking, opaqueness can be a bit daunting at first, right? Especially if you're not used to functional programming. If you're not used to functional programming, that can be its own ordeal. Moving from non-functional imperative programming to functional programming, that's its own thing. And then to double down on that, to make it even more daunting, I suppose, for some people, is the fact that it's all asynchronous as well. So you've got the movement of work across different thread boundaries to contend with as well, and that can make it difficult. And I know what you're thinking at this point. Gee, what could you do to make this more difficult, Josh? I mean, it sounds like this is going to be one heck of an uphill climb, and I don't think that's true. I think it takes a little practice and a little muscle memory to appreciate the tool and the API, and to start writing code and just to see that, yeah, it works the way you think it does. And most of the time, if you don't know how it works, there's a friendly community or there's a self-describing method you can call or something like that. But it can be, I suppose, daunting, right, at the very first, especially if you haven't done either of it, and you might be thinking, gee, I'd rather move to the surface of the sun. I mean, that seems easier. You might as well ask me to do that, but it's not so bad, right? Okay, let's talk about some of the obvious stuff. Okay, so I've got an application. It's going to be a event listener, and in the event listener, I'm going to listen for an event, the application ready event, and this is just me starting up. I'm just waiting for the application to start up, and I'll run some code, and the code is just going to be trivial demo code that we'll work with here. Okay, so let's see some of those opportunities here. First of all, let's say that I want to generate a stream of data. So I'll say flux.generate, or actually better yet, flux.just. And what I'm doing is I'm creating a reactive type here. Okay, I'm creating a publisher that supports 0 to X records. That's a flux. Monos support it's a reactive type, and it supports 0 or 1 record. Okay, so these are both from Reactor. They both implement the publisher interface from the reactive stream specification. They both publish streams of data to subscribers, and those subscribers can be on different threads, and the publication of the data can also happen on a separate thread. So I'm just going to create A, B, C, D, E, F, okay? Just a stream of letters. And now what I want to do is I want to log. I guess the most obvious thing you can do to debug stuff is you can use subscribe, right? And you've got subscribe, and subscribe is by default, if you use the reactive stream specification implementation, subscribe takes a subscriber, and subscriber is a bit of a verbose interface. You can see that here, right? So subscriber, and then there's on subscribe, there's on next, there's on error, and on complete. I don't want you to be in the business of writing subscribers. You probably don't need to most of the time. Instead, use one of the overloaded methods. So here's consumer, and that takes the string parameter, which is the letter, that we've expressed here, and it allows you to do something with it. So I should have brought Lombok. Oh, I already regret it. Okay, private final. You know what? I'm going to bring in Lombok. I'm that kind of guy. I am that lazy. I'd rather add a dependency than write the extra code. So log4j. No, wrong one. Lombok. Good stuff. Okay. Did you see how I kind of like just sung? I just sung the word Lombok, and then almost as if by magic it kind of appeared. That was kind of cool. I don't know. Whatever. Anyway, log4j2. Thank you. Good stuff. Now there's my logger, and I can now log this out. New letter. All right, good stuff, huh? Good stuff. So there's this, and now I'm just logging the data out. But what if there's an error? What if I have some sort of error here? So let's say that I'm going to do a map. I'm going to say, okay, well, or better yet, I'll do a map, and in the map I'm going to throw an exception. Okay, so if x it's letter, if letter dot equals in a block, of course. Okay, equals f, then return. I'm going to do a flat map here. Then return mono.error. Illegal, let's say static class illegal letter exception. For some reason, I've chose to make it very hard to have the letter F in a stream. I don't know why. Whatever, it doesn't actually matter. We just want some sort of error case, okay? So we'll say new illegal letter exception. All right. And good stuff. Okay. Good stuff. So actually we don't even need that. Okay. So we're going to throw that. We're just going to assume if it's an F, it should always throw an error, and that's fine. Else, we're going to say return mono.just letter. So I'm going to return. I'll keep every letter except for F, which I, for some reason, arbitrarily just really don't like. Okay. So we're going to get rid of that, and we're going to keep mono. Letter otherwise. So good stuff. So now I've actually just flat mapped the data. I've got a pipeline. And by the way, this is what we mean when we say we've got a cold stream, right? So I'm actually creating a cold stream here, right? Letters. So there you go. I've got a cold stream. If I subscribe to it, suddenly it becomes a hot stream, right? I'm subscribing to it. You can actually take something that is a cold stream and turn it into a hot stream. So basically, a cold stream means that it's an empty pipeline and nothing is flowing through it yet. And so, it would replay the entire pipeline from the beginning. It would start from flux.just.a, and then FlatMap, and then, whatever, right? It would keep going through the operators. I could do filters and all that kind of stuff. It would do that each time you subscribed, for example, or each time you called .block, or each time you called any of these things that sort of, end up having the effect of pouring water in the pipes, basically. And that's when it becomes a hot stream. Now in this case, I've got a cold stream. You can actually take a cold stream and create another cold stream that's actually a hot stream, kind of. So for one example is that you can say letters.share, and in this case, it wouldn't replay from the beginning, because what share does is now when the subscriber subscribes to this, like this, share.subscribe. We can actually extract this out. String consumer. So now when we log the data, get stuff. There you go. So now when we log the data, you see that the shared subscriber will actually see possibly, you know, B only. It won't see A at all. It's actually going to get the live stream of data. Okay. One way I could guarantee this is by delaying the data. Right. I can actually stagger it out a little bit. So I can say delay elements duration of second 1, and then I can say thread.sleep 2 times this. There you go. And so now, in theory, I should only see, you know, maybe B, but possibly not, but, you know, C, D, E, F. That's right. So out of the shared one, okay? And that's because shared doesn't replay the entire pipeline. It's not starting the processing again. It's actually tapping into an existing sort of in-flight stream of data, okay? So that, I hope that helps. That's not actually what I was trying to show you here, but it does help you hopefully appreciate some of the benefits of, you know, assembly versus execution. Okay. All right. So let's run this. What do we get, huh? What happens if we run this program? Okay. So I got an illegal letter exception. No Fs. Can't be an F, right? I think that's fair. And you can see the error. You can see the exception there. Now, in this case, the exception is, in this case, it's managed to bubble up to the top. That may not always be the case. And so you will want to subscribe to the errors. You can actually process the errors. And you saw that before. You saw a subscription or subscriber from the Reactive Stream spec has an on-error method, right? On errors when we get any exceptions. But we don't have a separate control flow mechanism, right? This is any error is treated like data. It's just like another kind of piece of data, just like on next. So when we subscribe to the data in the on error, we get that data, and that stops the flow of data through the pipeline. It's not a separate control flow. We don't do try-catch because try-catch would be weird, right? Try-catch assumes everything is in the same thread of execution. That's not what's happening here. And so errors are handled in the stream itself. We have an overloaded version of subscribe that takes that handles errors. So you can see the second one is given a throwable log.error. Okay. And of course I can get rid of that because it, you know, we know it will never make it that far. So good stuff. Actually, it occurs to me I could, just for our demo here, make that simpler. Ah, that's nice. So now I'm saying log through, and we don't need the shared version. Keep our demo simple. Okay, so now we are, I guess we could actually have a, let's see, void error throwable t log.info, oh no's, and then log.error t, okay? Okay, that's this. So I'm going to now change it to this instead of log, and then that'll be everything else. So we start this. Okay. So there it is, right? There's our oh no. So that's the most obvious opportunity for us to work with and interact with errors. Now in this case, I've got, you know, everything's kind of just straightforward. It's a single thread, really, at this point. It doesn't seem like it's moving across different threads. But you could move it across different threads, right? You can actually say, I want to publish this on a different scheduler. Right? So scheduler dot elastic, right? So we could do that. Now what does it look like? Can't be an F, lambda, FlatMap on next, debugging this. It's not exactly clear. Did that work or not? Did that actually spin up a separate thread? I suppose I should be logging the thread data. So you can actually move execution from one thread to another, or you could do, instead of publish on, you could say subscribe on. Right, so I'm gonna schedulers dot elastic, and then the second parameter is request on a separate thread, true, and we'll run this again. Okay, so in theory, the pipeline, the thread of execution, and actually we can see that here. In theory, the thread of execution is on a separate thread than the thread on which this was launched. Okay, I don't have any loggers to see that. Let's see what's the best way to do that. Let's put a method here. Void info string letter log dot info. The current value is letter. Okay, and I want to log also the name. So log dot info thread dot current thread dot get name. We'll do the same thing for the error. Alrighty. So there's this. Okay, so there's my updated code. Let's restart this with this instead of log info. Good. Restart. Okay, so you can see now, yes, thread for the first, at some point we're on this thread elastic 2, and we stay on elastic 2, and that's when we log out the error. We don't have the other items in the stream because this first stage gets run first. So basically, we're moving across different threads, right? We're moving on to different threads of execution for the processing of our data. So what would a stack trace look like, right? What would a stack trace look like if we actually threw an exception? What if I had a null pointer? What would that look like? Let's try that. Okay. So instead of doing a flat map, which is a nice organized way to do it, let's do dot map and L, and I'll return L. I'll say return L, and we'll say if L dot equals F throw new null pointer, or actually leave a letter exception. Okay, so there's this. Okay, so that's basically the same result, right? We can actually see that as well. Number of different ways to sort of see the data move through the pipeline. We've created FlatMap, and I processed an error. I've got, and here I can actually, if I wanted to, I can include information about the error in the error callback, right? Whereas with this, I'm just throwing an exception, and the framework captures it, and it bubbles up in the same way. But I still don't have a great picture for, you can see I've been trying to kind of feel out where the data has been going and how it's coming together and why it arrives. I can see the error here. I've been very good about adding this exception, haven't I? I've been very good about documenting what's happening here. I've got these callbacks and, really trying to give myself as much information as possible. But I don't, if you looked at this right here, you wouldn't have an appreciation for this or possibly any other steps before it, right? Let's say I did map L.2 lowercase, right? So now what? Let's do that. Okay, so now we have the extra step there, and we're logging that out. EF, oh, it's lowercase, so that actually gets through. Let's try that again. Sorry, wrong test now. Lowercase, just in case. In case I get back into that trouble. There we go. So we got the same issue. You can see that we got to the same error again, But we didn't see that there's several steps before. We don't know how this thing came together. We don't know what the assembly of this pipeline looks like. And without that information, we have no context to use in debugging this. We have to kind of just puzzle at the code itself. So one way you could do this is to, I suppose, add debug information, as we did kind of with the logging and all that stuff. Another way to do that is to call .log. So let's say .log, and you can even plug in a logger or a category or whatever if you want. I'm just going to use the default. Let's just rerun the same program. Okay. So here you can see that we can see what happened. We can see, oh, okay, the subscriber subscribed and was given a subscription, right? And then we are requesting a buffer. So by default, the subscriber that we are, the wrapper around our consumer is a subscriber that then requests 32 more records at a time. It's a small buffer. Obviously, we don't need 32 records. We've only got, A, B, C, D, E, F, right? And we can see that it processed on next up until E, and it finally got to an on error when it came to something, and we know that it's an F, right? Obviously, our exception is fairly well self-documenting. So that log information, we added that to the end of the pipeline, and that gave us information about what happened, right? That's not bad. By the way, instead of doing the subscribe, instead of doing that, if you don't want to, right now, I'm doing the on error thing here in the subscriber, but that's not always the case, is it? I might actually give, let's say I want to have a method here, right? So void process publisher, right? And this will be a publisher of type string. Could have been letters or cars at this point. I realize that now, but hashtag YOLO. Okay. So now what I'm going to do, I'm going to say letters.subscribe. Do I have to make the user worry about that, right? What if I want to have a built-in thing that handles errors in the publisher, right? So here I'm going to, let's see, if I do this, letters.pub, whatever. And so this is the thing that's actually processing the data. I don't know where this publisher came from. I didn't, I don't want to have to ask the user to remember to call the on error consumer to provide that when it uses this. So one way to do that, to build it into the pipeline, is to add it as an on error, do on error callback. So here I can say do on error, and you get the same opportunity. Okay. So this dot error throwable. Same exact code. Cool. So now this is no longer required. It will have an on error callback, no matter what, whether the subscriber knows to provide one or not. So if you get an error, you can have some generic behavior in there. You could actually contribute like some sort of pre-processing that looks at all publishers that are created in your organization, and that then instruments it to do the right thing there. So lots of opportunities, good stuff. Okay, so we're back to where we were. We can see that with the log operations, we get visibility into what's happening. I like that, but I am also leery of the fact that this Stacktrace isn't really helpful. I mean, it is, in this case, it seems to be okay, but if I moved work from one thread to another, if I did things like that, if I had parts of the application if I had parts of the interaction that happen on different threads, then things would become kind of difficult, right? So let's say I wanted to now get a better view of the assembly Stacktrace, not just the Stacktrace. So again, keep in mind, we've got the assembly of data, right? That assembly of data pulls together our execution that happens across different threads. So I don't want a Stacktrace. A Stacktrace doesn't make any sense. Stacktrace is by definition in a single thread, right? I want the execution. I want the error that shows me the graph of how the error happened from the very beginning across all the different threads all the way to where we are, right? Which is more than a thread Stacktrace. So in this case, I have a couple of options here. I can use hooks. Oh, by the way, before I forget, I didn't mean to forget one thing. You can also do this. You can do checkpoint, okay? And so you can actually say, I want an error to show this message, and I can say force a stack trace, okay? So when it gets to this part, it's going to force in this pipeline, at this point in the pipeline, it's going to log out the data, log out a string, and then log out a stack trace. So I can say, okay, log out, capital letters, okay, lowercase letters. Okay, so I'm giving myself breakpoint information here. Let's run this. All right. So okay. So we get to this final checkpoint here. That's the last one. I guess that's the one that gets shown here. So we can see I want an error to show this message. There it is. There it is. There it is. So you can see that we get this like output. I guess the last checkpoint is the one that gets honored. I'm not really quite sure about that. Oh no, that's why it's confusing. It's got the I said both. I told both to show me a stack trace. So actually I don't need this. Let's see what happens without those. Okay, checkpoint. So this is the only checkpoint. Is that better? Did I actually show less stack traces? I feel like I have the same number of stack traces. Okay, anyway, I didn't mean to get lost on that. All I'm trying to say is the checkpoint is the thing that shows errors. It shows up after there have been errors. So this is the first checkpoint by which there's an exception. Okay, so this is the one that we see. I've got checkpoints here, and if there had been errors in this or this, then we would have seen these checkpoints. Okay, I'm not sure what the show stack trace thing is buying me actually. That's why I was a little confused. Either way, we've got checkpoint. That's very useful. But I still want the assembly stack trace. That's what I was trying to talk about before. I want the ability to see the bigger picture. I want to see how things assemble in such a way as to arrive at this particular error, this particular sort of congealing of data, of stream data, to arrive at this particular kind of error. So one way to do that is to use a hook that you can add for reactive code. So you can say hooks.on debug or operator debug. Okay. And then you restart. Okay. So now, much more useful. You can see that here's the exception. Okay. Go down. We can see the trace, so we can see that the error happened in the map operator, right there, right? There's no disconnect between where this came from. And actually, I think it would be more useful if we showed this version, just so we can understand that we're pulling data down from a particular place. Let's try that again. Oh, nope. If letter equals ignore case. Keep that commented out. Okay, so here we have same thing. We can see that FlatMap is where the error happened, right? And we can see the method influx.java that corresponds to FlatMap, and we can see that that was invoked in Go. So again, there's no guarantee that this will happen in the same thread as Go, right? We've in fact, quite the contrary. We're pretty sure it's not going to execute in the same thread as Go, right? and yet we can still see that it started here and then it ended there. And the reason is because we have this hooks on operator debug. That information shows us, at first it shows the exception first, which in some helpful information, and then it shows us the thread stack trace, that is only the flow of execution on a given thread, which isn't super useful for reactive programming, but the following section provides information about the assembly trace of the publisher. So here we can confirm that the error was first generated in the FlatMap method, which then of course links to the go method, right? The operators in the third section we finally see here where it was observed, right? So we can see that the operator observed the error. We can see in this section the operators that observed the error after the error was first triggered, and in which user class they were triggered and chained. And the way we do this is actually by adding a lot of extra weight to the publisher, right? So basically, there's a lot of instrumentation, a lot of extra information that has to be created. Basically, we create an exception. We create a stack trace for each operator, and then we attach it to the operator, and that gets perpetuated. And so then later on, when something goes wrong, we can call all that together, and then use that to build up this assembly graph. But that's a lot of runtime overhead. Okay, that runtime overhead may not be desirable. I don't think it's desirable in production, for example. But you still want this information. This information's really useful. So we have an agent-ish kind of thing. I don't think it's technically, strictly speaking, a Java agent, but it has the same effect, which is that it pre-processes the code of the application in the class loader before the application starts up. And that's called the Reactor Debug agent, and you can add it to your build if you're using if you don't already have the milestone or snapshot dependencies, make sure you do. We started with our project on start.spring.io using spring snapshots and spring milestones. And so with that in place, all I really need to do is to add the Reactor Tools dependency. Okay, and this will, I hope this will get merged into the main of Reactor Core later on, but for now it's a separate thing, not a big deal. Okay. All right. So dependency. It's Reactor Tools, and I did this once. Don't do that. It's not .tools. It's IO project reactor. That's it. Okay. .m1. You add this, and then you install it. So now instead of doing this, I can say Reactor Debug Agent .init Reactor Debug Agent .process existing classes. This is good. In theory, I don't need this for my application, but I'm gonna go ahead and leave it there anyway. Okay, I think I do need it. I'm not sure why. So okay, we're gonna hit run. Like in theory, you can do this later on. For example, after public static void main has started. So you've got existing code that's started in the application, and you don't need to do this if you do it before. But I think you do. It seems like I need to for my Spring Boot stuff. So for your purposes, just do this. And worst case, it's a slightly extra slower on the startup. Okay, so there you go. There's the actual. There's the whole stack trace, right? This is the actual. And what this does is it rewrites your publisher, your reactive stream, and sort of bakes it in at the bytecode level, right? So that's cool, right? You've got now the same kind of information as we had before. Without having to build all that extra information at runtime. So that makes it faster. And in theory, you could actually take that into production. Obviously, you should change your logging accordingly. I like the Reactor Debug agent because it just gives me safety. It's a fairly good middle of the road compromise between extra runtime information and slightly slower startup time. But in exchange, I get much more insight, and I don't pay a real penalty there. One thing that people often ask about is, well, how do I know if I'm writing truly reactive code? What if I'm dealing with something that that in turn blocks, right? So, how do I make sure that that's actually working as I expect it to, right? If I've got reactive code and for some reason it's slowing down, or I'm getting memory starvation, I'm running out of threads, that tells me that something in the pipeline isn't playing fair. It's actually stealing time on the thread when it should just be as quick as possible, right? The whole point of this reactive paradigm is that we don't have a lot of threads because each thread is an event loop. You've got a selector thread which then dispatches to some other thread, and you do the work on there very quickly and you get off, right? So you have very few threads in total, and this only works if the work you're doing is asynchronous I/O, and that can be done off thread, basically. You will find that if you try and integrate blocking code into your API and then you try and deploy that, it might even work. This is the most insidious part. It might even work in your development environment, but when you deploy to production, you'll notice that you're starving for threads, right? Because you've got scale now, right? And so this is where you've got to be very careful. So we have a really crazy, amazing piece of software here called Blockcount, developed by one of our team members, Sergey. Blockhound is just insane. It actually does some native code as well, but it doesn't, it's just done so eloquently that you don't need to worry about that. So here's what I'm going to do. I'm going to install Blockhound like that, .m3. So that's under Project Reactor Tools, not in the same package as Reactor Tools, which is a wee bit confusing. And you bring that in by just saying blockhound.install. So here I'm gonna, actually it doesn't matter, I guess. I haven't even, I suppose that's probably fine, but for now keep it simple. One less thing to look at. Blockhound dot I feel like yeah, should just be Blockhound. I am confused. Okay, let's see. Go to this one. Yeah, it's there. Maven re-import. I could have sworn I already set that up at some point, but let's just see. Well, that's confusing, isn't it? So we're looking for the right version of Blockhound. I've got IO Project Reactor Tools, Blockhound 1.0 M3, and I've got the snapshots. Maven clean package. Seems like that should be there. Blockhound. Oh, there it is. Okay. Now we're cooking. So I just had to, I don't know, shake a tree or something. It's now finally working. Good. Okay, so now I've got blockhound.install. This takes a Blockhound integration, and there's actually different, you can use Blockhound without Reactor. It detects blocking code anywhere you want it to, right? There's a default Blockhound integration that gets loaded and contributed automatically for Reactor, right? You can see Reactor Blockhound integration. There's also one for Arcs Java 2, right? And so you can use, whatever you want. There's a lot of different ones there. There's one for logging. If you have a logger that's blocking, you can detect that. By default, the one that's available for Reactor is already loaded because Blockhound uses a service loader mechanism. So you can see here in this package, it says meta-inf services Reactor Blockhound integration, and it just loads this class. So the Java 6 service loader API results in loading this class, which gets registered automatically, and that automatically registers the right integration for Reactor. So you don't need to do that yourself, but you could provide other Reactor integrations here. You can actually override or whatever, or you can just leave it like that, which is the default, which is what we're going to do. And now we're going to change our code here a little bit. We're going to actually create a blocking API. Okay, so let's get rid of the error. So we can, let's just, well, here, actually, let's just comment that out. Good stuff. All right. Good. So now I'm just returning the letter always, okay? There's no error. It'll never be a problem. Everything will continue happily, and we can focus on bigger, better things. Whoa, what happened there? Good stuff. Okay, so now I am now going to block. I'm going to create an API that blocks. Now keep in mind here, I'm subscribing on a different thread. Okay, I'm subscribing on a different thread pool. That scheduler is what allows Reactor to figure out on what threads it can run this code. Now, when you use a scheduler in Reactor, schedulers are backed by usually thread pools of some sort, but there are different kinds of thread pools. They're not all created equal. Okay, so if you're using Elastic, for example, then sorry, if you're using Elastic, the scheduler Elastic, this is meant to scale out, right? This is a scheduler that's meant to scale out as much as it needs to. And so the whole point there is I have something that's going to block, and thus is going to necessitate the use of more threads. And so I'm fully prepared for this to scale out, or as much as needed. I'm fully prepared for something to block. So if you have something you're going to do with a JDBC data source or something, then you use the Elastic scheduler, because it'll do the right thing there. Okay. Obviously, this means that your application is now constrained by your ability to handle to add more threads. You've lost a lot of the big benefits of using a reactive API. Okay. So cache in turn creates a thread pool. Where's all this code? Schedulers. Let's see. Not blocking. Non-blocking. Yeah, instance of non-blocking. And you can see, find usages. Some threads that are created by thread pools that are blocking, or rather that are not blocking, those threads will descend from another class that in turn has this interface, and you can detect that. Okay, so if you're wondering about which schedulers are blocking and which ones are not blocking friendly, this one's a blocking friendly scheduler, so this won't cause any issues. But let's say that I want to have one that will error out, right? Something that will definitely cause an issue because it's limited. It's not going to create new threads ad infinitum. So here, I'm going to create a thread pool limited to 10 threads. Actually, you shouldn't have more threads than you have cores, for example, in this case. And by the way, by default, you've got a scheduler that is just constrained to how many CPUs you've got, how many cores you've got. So you shouldn't need to do this, but if you want to override that, you can. So here I'm going to say, okay, let's subscribe on this scheduler, okay. And what I want to do is I want to block. I want to create something that'll actually end up blocking the flow of execution. So in order to block, I'm going to create a method here called void block. And void block will just block. I'm going to sleep arbitrarily for a second. And this is going to be a thing that'll throw an exception. So I'm going to use lombok to just swallow the exception, or to hide it. So it'll wrap this in a try catch. And then I'm going to do a FlatMap. Okay, so I'm going to FlatMap, or I'm going to do a do next. That's even better. That way I don't have to do any work. So this block. I feel like that should be it. Good. Yes. Okay, so I'm just for each record that is consumed, I'm going to slow down the processing on the thread. I'm going to sit on the thread that we're using on the thread pool, and that we know that thread pool is going to be a can't block thread pool. Each thread in this new parallel thread pool is, there's only 5 threads. So if you're blocking, somebody's going to be starved eventually. As soon as you get 6 requests, you're not going to be able to use that. So the Blockcount will detect that for us. Let's try it out. Cool. Got a lot of errors. We should blocking call. There you go. Java line error blocking call, and you can actually see that in turn turned into an error in the pipeline, which the rest of the error handling code that we put in actually catches. So that's kind of cool. So there you go. So you can actually see this is where we're spending our time. Somebody's making a call to this, and we can see that Blockcount has instrumented our code there, and we can see that it's actually happening in block. Isn't that cool? So now we have the ability to find where we're blocking in the pipeline, right? Even if it's somebody else's API and it's blocking. Now let's just to show you what I'm talking about. Actually, let's change this. We'll do this a can block. So elastic. There you go. Let's do can block. Okay. Restart this. So there you go. Now that's behind the scenes. We're creating a new thread. You can see it says right here, thread 1, 2, 3, 4, 5, 6. And it would, if I had a trillion records, it would keep trying to create new threads as long as it needed to process the data, right? Because, we'd run out of, we would have everything, we'd be using all the other ones at any given time. So that's not a good approach, and you should be careful about that. You should test whether that thread that you're running on is elastic by using the scheduler is blocking threads, right? Okay, I think that's it. I think we've covered just about everything I can imagine wanting to show you. I hope you got something out of this. I hope in our journey today you saw some tool that'll help you out. Basically, the reactive debug agent and Blockcount are your friends. They're agents. They actually pre-process code. They're bytecode, right? They work at the class loader, if you will, level, not at the runtime level. So they're actually fairly efficient. I can't say that they don't add any overhead, but they're better than not having a way to discover the errors, certainly. And even if you only use them in development time, there's going to be some benefit there. And if you use them in production, you know what you're doing, and at least you have the ability to recover. It's all about how you can gracefully degrade. I think these APIs are really powerful, right? This is not much more complicated than a Java 8 Stream API, right? You're not actually doing things that are much worse or more complicated than the Java 8 Streams API. It's just that you get better scale, right? You get better scale than if you wrote synchronous or blocking code. I appreciate you listening, as always, and if you like this, please obviously leave a thumbs up or a comment on the video. And as always, thanks again. We'll see you next time.